Welcome to Closing the Loop, a podcast presented by Lakeside Process Controls, where we connect you with experts, end users, and suppliers in the industrial automation industry. My name is 𝗧𝗜𝗠𝗘, Business Unit Lead for Measurement Solutions and host of the show. Each episode will be featuring guests from Lakeside, Emerson Automation Solutions, and other industry leaders. We hope that through these conversations, we can close the loop between your current knowledge and the latest advancements in industry. Our goal is to educate you and provide you with ideas for both improving efficiency and safety throughout your facility. And with that, I'd like to introduce you to today's guest, none other than Emily Stone. Welcome to the podcast.
Well, thank you for having me, Justin. I really appreciate it.
Yeah, I heard that you were very excited to be on the podcast. You were counting down the moments and hours, and you were like, when are we going to do this? I'm ready for 3 hours at least. Is that right?
I was sitting outside the door waiting for you to let me in,
well, here we are. We have over 4 hours ready to go, or maybe a little bit less than that. So why don't you just introduce yourself a little bit, where you're coming from, maybe why you were here this week, why you're on the show, and then we'll go into a little bit of your background.
Fabulous. Yep. So Lakeside does these fabulous STEAM seminars.
Nice.
Where we can work with our customers and help to educate them on how they can improve their systems.
Yep.
And so I got asked to come and present on the Fisher controls and Desuperheater side of things and steam conditioning. So that's what we're here this week doing.
And we had a great time so far. Lots of turnout at our Mississauga one, and then tomorrow we're headed to Sarnia. So we got a little bit of a road trip tonight. Woo! Jam-packed day today, so none other than fitting in a great episode on the podcast. So maybe you can give me a little bit of background. We talked about this before where you said some people were going to have a hard time guessing your accent. So where did you grow up? Where are you from?
So I was actually born in Stratford-upon-Avon in England, in the UK.
Yep.
And then moved to Chicago. Shout out.
Chi-town.
And then from there went back to university and got an engineering degree down in Rolla, Missouri.
Oh, wow.
So that's where the Missouri is coming in. And then now I work with Fisher Flow Controls up in Iowa.
Oh, that's fantastic.
And what accents a little bit of everywhere.
I was going to say, yeah, that especially with the English to the Chicago to the and then what did you study in school?
So I actually studied engineering management.
Oh, look at that. Okay, totally applicable. That makes sense. And then how did you end up in Iowa?
Fisher.
Oh, is that right?
Yep.
Okay, it just attracts everybody out there, right?
Yep. We have some really good alumni from my university. So
I've never been. So how far from where you went to school versus where the Fisher factory is? Like an hour, 2 hours, 10 hours?
Oh, it's about 4.5 hours north.
Okay, so not
too bad.
Okay, well, at least in Canada, 4 hour drive. I mean, it's not great, but you'll do it.
I mean, the joke about Marshalltown is that it's the middle of nowhere,
yes.
But it's the middle of everywhere, because every city is only 4.5 hours away.
That's funny. Yeah, only 4.5. And I hear the drink of choice is Busch Light. Is that correct? Or sorry, Busch Latte, as I've been corrected. That is correct. Okay. So these data points are not skewed. Okay.
Nope.
So I know a thing or two about Fisher then, clearly. At least I know the beer of choice.
Exactly.
That's awesome.
The pub to go to is the Old Timer.
The Old Timer. I keep hearing about a steakhouse. I feel like it's called Roofs.
Ooh, Rubes.
Rubes. Oh, my mistake.
Best steaks you've ever had.
Oh, well, then I'm going to have to come down and learn a thing or two about Fisher. Yeah, we've got an Italian restaurant at our factory, and that's where we go, and we call it, I don't know what it's actually called, but we call it the Pope's Table. And so you quite literally have a busk of the current Pope, and it's a table that rotates around. Everybody sits around it, and then you order Italian food, and you pass the food around in a big circle. And so we call it the Pope's. I don't know what the restaurant's called. Great Italian food, and great way to just, I guess pre-COVID it made a lot more sense. Now that I think about it, it might be a little bit, everybody's picking off the plates, but that's okay. So tell me a little bit about your role at Fisher and how long you've been at Fisher, what you focus on, or I guess Emerson is the most appropriate way to say it.
So I joined the Emerson family 6.5 years ago now.
Okay, great.
And so I joined our global industry sales group.
Okay.
So originally supporting the chemical team, and then I moved into the power team.
Okay.
And so what that does is when you guys at Lakeside get really complex problems, or we're trying to do something that hasn't been done before, you can come and ask us questions as the factory. And so we can work out what is physically possible and what's not physically possible.
Gotcha.
And then about a year and a half ago, I moved into what we call the severe service team. And so that's where we go into more of the fun theoretical
Oh,
stuff.
really? The modeling and the theoretical. Wow, that's pretty exciting.
So everyone's super excited about supercritical valves.
Yes.
And so we're actually working on sizing and selecting and developing those techniques for the rest of the industries on how to size and select those products.
Okay. So this is for very specialty applications then. So this isn't just standard steam. This is these, powerhouses and those. Okay. I mean, I like to think that everything I do is supercritical. So I didn't know that this was a special term for Fisher or severe service. I hear that passed around, and as a measurement individual, you go, when am I going to learn severe service? Is everything I do just severe? So that's probably my first question for you is how do you define severe service? Because to me, a lot of stuff we get into gets pretty severe. So are there physical definitions, or is there a gray area?
So we bucket things into severe service and general service.
Okay.
General service is about 80% of the industry, and that's where process comes into one side of the valve, takes a pressure drop, nothing too scary happens, and then it exits the other side. Fabulous.
Gotcha.
Materials can be a problem depending on what the process is, but nothing too scary happens inside the valve.
Okay.
Sometimes things get a little odd, and that's what we call severe service.
Gotcha.
So if we're looking at a process coming in, and then it takes a phase change while it's in the valve, so the pressure inside drops below the vapor pressure of the fluid, and then recovers. That's something that we call cavitation. That can cause other damage to the valve and product, and so we want to try and stop that damage from occurring so that you don't have to increase your maintenance cycle. Nice, right?
That's a good point. But do you ever run into where you have a phase change and that's intended? Okay, yep. And that's totally fine. That can happen?
So if a process comes in, it takes that pressure drop, goes below the vapor pressure, and it stays below the vapor pressure, those intended drops. That's something that we call flashing.
Gotcha.
And so that is definitely intentional. And damage can occur from that kind of thing, but we have techniques and models to help us understand what kind of damage is occurring, how severe it's going to be, and then how we can stop that from hurting your process.
Okay, and then so for some valves, it might just be an unintended consequence, and that just reduces the life expectancy. But that's just there's no way around it in some instances, right?
So if the intent is a phase change, that's flashing.
Yeah.
If it's unintentional phase change, that's where cavitation comes in.
Okay.
And it flashes internally and then reconstitutes on the backside. And that reconstitution causes a different kind of damage.
Gotcha.
So
okay. And then you can try to build it because you know that this application is going to probably see that. And okay. I remember walking around, I think it was a pulp and paper mill, and you could, I mean, the account manager was telling me, that valve is definitely cavitating because you could hear it. I think he said it sounded like the sound that he described it as was almost like rocks traveling through. And so it didn't sound good.
Yeah, no, it's strange. If you've never heard it, the moment you hear a valve, and it legitimately sounds like rocks tumbling through a valve.
Yeah.
If you've ever watched those TikTok videos of people actually intentionally
the rock tumblers,
rocks, that's exactly what it sounds like, just funny. Going through a valve.
Yeah, it doesn't sound like it's good. Yeah. Okay, so maybe let's step back a second here, because I've already assumed that I know what a valve is, but I think I know what a valve is, but I want to hear it from you. So what you've described a little bit to me sounds like a regulator. So can you help me understand the difference between a regulator and a control valve, maybe the pros and cons? I know you're probably more on the valve side than the regulator side, but when I think about pressure drops, I instantly think of, intended pressure drops, I think of regulation.
So the best way to describe the difference is that a regulator is taking a process fluid that may have some fluctuation in its pressure, and it's trying to meet a specific pressure at the outlet. So if you've got, say you're pulling in water from the river, it could be at atmospheric pressure, it could be flowing downstream, and you could be higher than atmospheric pressure, but you want it to be at a very specific set point.
Yes.
Downstream. Now, a regulator will take any inlet pressure and regulate it down to just that one specific outlet pressure.
Gotcha.
Whereas a control valve will take any inlet and almost any outlet. And you get that option of, hey, I want the inlet to be 2,500 PSI, but I want the outlet to be 500 PSI, 1200 psi. Depending on how I'm trying to operate my plant or what I'm trying to do, there might be some variability. And that's why you would use a control valve as opposed to a regulator.
And you can change that on the fly too, right? Like with a regulator, it's, as I understand, you have springs and like that's fixed, right? And you're going to get 30 psi on the outlet. That's what it's going to do. But if you want 32, you got to maybe take it out of line and rebuild it, versus the valve has that ability to adjust that okay. So that makes more sense. But so you still can use a valve to drop the pressure. And I guess you're always going to drop pressure because you're reducing the cross-sectional area of the pipe, right?
So my best example for control valves are actually ones that you see in your home. So you probably have a sink at home, I'm assuming, either in the bathroom or in the kitchen.
Like 5.
Well, a lot of sinks these days have the arms that you can lift, and so you can control how much flow is coming out of your sink. Now, same thing as a control valve. We have that variable orifice, and so as you lift up the handle, you are opening up more of your piping, more water can come through, and if you're going for open it just a small amount, you can see that flow comes out really fast because it's got that high pressure and low area. You see higher velocity.
Gotcha.
As you open it up, you get more flow, but sometimes less pressure.
Yeah.
Same kind of thing in a system, but we work at significantly higher pressures.
Yeah. It's kind of like as a kid, I probably will do this summer when you get the hose and you put your thumb on it, and same kind of principle applies there. I always think about, we do a session on intro to process controls for some of our new hires, and I often talk about your shower. And so I never had thought about it from the valve side. I was thinking more about just process controls, where I say, well, in your shower, you can't control the temperature. Like you don't say 105 F, right? You adjust the knob, and that adjusts how much cold and hot water are mixed together. And then that's also why someone flushes the toilet and all the cold water goes to that toilet, and all of a sudden you're burning hot, and then you adjust it, and then you go through this oscillation process and adjust it: too hot, too cold, too hot, too cold. So same kind of idea, I guess. But I guess that might be like 2 inlets. Is that a 3-way valve? Is that what those are about?
So yes, that would be a 3-way valve.
Okay.
Or if you've seen desuperheaters, you're getting close to what a desuperheater is.
Okay. I do want to talk about that because that's something that I hear that word thrown about. And so I think we understand a little bit about control valves. Obviously, there's some variability and regulators. And then severe service is just these, more complicated valves. Yeah, then where does this desuperheater pair? Like, how does that fit into things? And is that only steam, I assume?
So desuperheaters Desuperheaters are a specific application for a product called an attemperator. Okay. So an attemperator is, by definition, a product that introduces a secondary source to an initial source to create basically a mixture, typically to control it down to a certain temperature. So some chemical plants will use them to introduce other processes into their chemicals, and they're attemperating. No steam required. Okay. If it's used specifically for steam, then we typically call those desuperheaters, because we're trying to reduce the heat in the steam. Okay. So it's a desuperheater. We're removing the superheat from the system.
Bringing it to, like, say, saturated.
Yep. Exactly.
Okay, so then that makes sense. So if it's not steam, so if I guess you're adding in a chemical or something, then so it'd almost be like you're spraying with that chemical into that line, essentially. That would be the same.
Yep. So what they look like in practice is basically you have your main process flowing through your pipe, and then you will have this attemperator or desuperheater, depending on the application, and that will spray this other secondary medium into the primary medium in order to produce some kind of effect. Gotcha. So whether it's some kind of mixing effect or whether it's a temperature control effect, sometimes you're just trying to add additional steam into the system to increase velocity. There's a whole bunch of things that you could use it for. Okay. But in essence, it's just a nozzle.
That's okay.
Just that simple.
So it's just got a big fancy name for nozzle. Yeah. So I guess on the desuperheater side, you have steam that has been superheated, and you add in, I guess, cooler water to drop that temperature down. Now, that makes sense to me. Where would the superheat come from upstream of that? Where can you talk through some of the situations that would create superheat? Because when you get steam from a boiler, isn't it just saturated? Ooh. I guess it depends on the
So yes, typically in these applications, what you do is you have water coming into your initial system. You heat up your water using something like a boiler. There are other options available, but boilers are the most common ones. You're going to take that water, you're going to heat it up as much as possible. Typically try and make it as efficient as possible, but you're trying to heat it. The main intent is just to get it hot. Yeah. Hot and stable. Yeah. Now, we talk about phases a lot. When you're in school, they teach you that there are 3 major states of matter. So you've got your solids, you've got your liquids, and you've got your gases. Correct. So water coming in is our liquid, and you try and heat it up to steam, which is our gas. Yes. If you... we're trying to heat up that gas as much as possible to make sure that it is stable. Yes. So hot steam, you want it to be dry. Yeah. So you want to heat it up, get rid of all that excess water that could be stuck in the fluid. Yeah. Now that means that it is superheated steam. If you are looking at a wet steam, that's when you've got condensate stuck in the system. That's when that water can fall out of suspension and cause damage to piping. Gotcha. So if you think about a kettle, kettle at home, you put water into it, you heat it up, there's induction coils, and you get nice boiling water internally. Yeah. But then you have that spout at the top that steam can come out of. Gotcha. If you put your hand over the top of it, that small temperature drop can cause water to condensate on your hand. So we're trying to heat it up so that that doesn't happen during the piping, because power plants are big. Yeah. It's got to travel through quite a few feet of piping before it gets where it needs to go. That makes sense. And so what we do is we get it all the way, we heat it up as much as possible. Yep. We get the steam to almost where it needs to be, and then we desuperheat. We take that temperature down, and we reduce it to just the saturation point. So just before it has that phase change and condenses. And then it goes through the turbine, or it does what it needs to do at that saturation point. Yeah. Because that's where we can optimize the amount of energy that we can get out of that steam. Okay, this makes a lot more sense. So superheat it, transport it to where it needs to go, desuperheat it, throw it into the turbine, as we like to say in Canada, and then obviously you go generate your process from there. Okay, wow, that actually really clarified things for me. You know, sometimes on the instrument side, you kind of have this narrow focus. So that's okay. So I don't think I wrote this word down correctly, but I think a temperator. That's what you said. Okay, so for the attemperators that are not desuperheaters, can you give me an example? Because I'm just curious, like what chemical would you be adding in? Like, I don't know. Can you give me an example? I'm curious what that looks like for not steam. Ooh, a lot of times when we use them, that's customer proprietary information. So I'm not sure I can share that one, but it's a good question. Yeah, depends on the customer, but the idea is still the same. They have some sort of gas that's flowing, and they are putting in some sort of liquid phase to it. Okay, and then the idea is that the liquid becomes in the gaseous phase or it depends on the... So it doesn't even need to be a liquid as an inlet. Oh. So we do have attemperators that are designed to use steam and that liquid as well. So so one of the really cool things that we have in the power industry at the moment, we're trying to go green as much as possible, improving efficiencies. So a lot of power plants are used for peaker energy, which means we've got base load. Up here in Canada, I know you love... we use nuclear power for a lot of the base loading. Yeah. And then when it's freezing cold outside like it was today, everyone turns the heating on, which means that you need more energy out in the grid. And so peaker plants can turn on. Gotcha. Now, it takes a lot of energy to get a power plant up and running, or even just a section of a power plant up and running. Okay. And so instead of, if you know that the cold weather's coming, you can set the power plant to operate at a lower load, so it's not really producing much power, but it's staying nice and warm, so it's a lot easier to get up and running. Gotcha. And it's more efficient overall because you're not wasting energy heating it up from freezing cold to boiling hot. Gotcha. And so in those applications, you're going to be seeing lower flows, lower velocities. You're not trying to keep the plant super hot, so you've got a lot tighter temperature tolerances. You're trying to keep things low. In those situations, what we can actually use is a steam attemperator, which means that we use both water and steam mixed together into the steam line. Okay. And so you have less of that water drop out. it's a lot easier to, you're seeing a lot less of that water dropping out of solution, and you're able to control that temperature a lot tighter because you've got a less deviation between your inlet steam and your main process steam.
That makes sense. Okay, you know what? I'm going to have to give some credit to the Fisher folks. This is getting a little more complicated than I initially gave them credit for. I always like to joke with some of our Fisher folks here. I said, how hard can it be? It moves up and down. Sometimes they turn side to side. How complex can it be? But clearly there's some sophisticated applications here, and this sounds pretty exciting.
Mm-hmm. Yeah. And I mean, in Fisher, we joke, it's just water and steam. How hard could it be? It comes out the tap at home.
Yeah, how dangerous can it be? How hard? It's just water, right? Just H2O. Yeah, that's funny. It's what you got me thinking of, too, is I remember even growing up, the debate about, changing the house temperature. So like, especially in like the summertime, it was like, wow, we're leaving the house, just turn the air off. And it was like, no, like we got to keep it going. It's more efficient. And it was that debate. No, I'm not paying for that. And I'm like, well, if you have a hot house to cool it all the way down versus maintaining, until I became a chemical engineer, no one believed me. And then, so I knew it as a kid, but I think it was just selfishly as a kid because I didn't want to be in a hot house growing up.
Well, it's also like when you've got a car in the summertime.
Yeah.
If you have one of those screens in the front of the windshield, it stops the car from heating up as much, which means you're not blasting the AC the moment you get in down to as cold as it will go.
Yep.
You're just able to get in the car and turn it up a little bit.
Yeah. Actually, you had mentioned TikTok earlier, and there was a good tip I wanted to share because I swear, at age, I'm not going to say my age, but at my age, to figure out this tip about the car, I thought this was a little late. But so, the problem when you're driving your car and you put all the windows down and all of a sudden your hair's going everywhere, or you put one and it makes it, we both have a little shorter hair, but it messes up the hair, right? And so I learned this trick where, so you're driving, you put your window down slightly, a couple inches on the driver's side, and then the two in the back a couple inches down. And the way that the air travels through the car, it's a nice breeze without being overwhelming. So it's a little cold today, but last week we had really good weather and I was doing that. I felt like such a professional. So there's your pro tip. Not just instrumentation, not just control valves, also practical life advice for you. Yeah, so there you go. The more you know. So TikTok can be a beneficial. Well, we'll see if it's banned or not in the United States. Canada, we're still okay so far. So, So we've talked a little bit about steam here, which I think is great. Let's take a step to the side here and start talking about what is different about a steam valve, right? So a Fisher valve that's designed for steam, how does that differ than just water, right? Or chemical, right? Different materials, shapes, and so forth. You tell me, actually.
Okay, so typically when we're looking at water applications, water, as we were talking about, it comes out the taps at home. So that's going to be lower temperatures and it's going to be lower pressures.
Yep.
When we're looking at steam, we're looking at much higher temperatures, much higher pressures. And so that means that we're going to be looking at thicker wall thicknesses to make sure we can retain that pressure.
Okay.
We're also going to be looking at noise attenuation is a big issue with steam. So steam going through a valve can get rather noisy, especially when you're taking a pressure drop. Energy can't be created or destroyed. I think we remembered that from second grade. And so when you take that pressure drop, that energy has to go somewhere.
Yeah.
And a lot of times that energy goes into an increase in the noise that the system can actually see. So one of the major things that we see with steam valves is this noise. So
interesting.
We have to look at different trims inside. So rather than just having the process flow basically out your tap, like we were talking about, you have that spray setting on your sink at home or out in the backyard. You can put the different nozzles on.
Yep.
So we look at separating those jets out and allowing them to recover without making noise. And so we're able to get the noise down, and it works pretty well. So.
Oh, that makes sense. Mm-hmm. Okay. So the primary concern is obviously temperatures and then noise, right?
Yep.
So and then what impacts, I guess, the shape or really the pathway? Because I know that I think it's called the E-bodies, I feel like, and it like kind of does one of these like shapes as opposed to going through like a ball valve, which is just, I guess, could be straight is the direction path. I don't know, is that what you call it? But that's what I would call it, the path of flow. Like in a Coriolis flow meter, it's kind of that U shape or an N shape, depending on if it's tubes up or tubes down. And and why is it called an E-body, right? It doesn't look like an E to me. So these are too many questions, but I have them and I need to know the answers.
You're absolutely right. So a lot of times we don't want to be using a ball valve or a butterfly valve in steam applications because you still have parts of the trim that are in the center of the flow. And exactly like you were saying, it's high velocity, it goes straight through. So if there's anything in the center, it can cause damage to that trim itself, which means that you're not going to get shut off and it's not going to work as well as you want it to be. So for those high pressure, high temperature applications, we try and stay away from those. What we'll do instead is use a sliding stem. So that's where the stem goes up and down. And just like you were saying, the flow goes in kind of like a Z direction. Yeah. So it goes in and then it goes either up or down through the trim and then it goes out the other side of the body. So that's what we typically like to do. If we've got high flows, then we might need to look at something called an angle body. So it comes in through the bottom of the trim, goes past the seat ring, under the plug, out through the cage, and then out the side of the body in kind of like an upside-down L shape instead.
Oh, okay.
So it's an angle. Yay.
Yeah. Oh, that makes sense. So if you see I had to draw it out.
So if you see an E-body, that's a globe body. If you see an EA, the A means that it's an E-body that's in an angle orientation. Angled.
Okay, but then there's this EZ. And is that where the Z comes from, or that's just one of the E-bodies?
That's just one of the E-body designs that we have. But if you see an EAZ, that's an angle body with a Z trim.
Okay.
So the way that we use naming conventions are, so the E-body is the design, and then the second letter is going to be what kind of trim we have. Is it an EZ, is it an ET, is it an ES, or is it an ED?
Oh, okay. That makes sense.
And so that means that when customers have issues, or if we are talking between Lakeside and Emerson, we can talk about the trim design without talking about the trim design. And if you tell me that it's an ED, I know what we're talking about immediately.
Okay, so I'm thinking I'm just going to bring it back to measurement. So it's like when I talk about the Elite Series Coriolis, and then I say it's like a 1/4 inch tube or a 1 inch tube or an 1.5 inch. It's like that's the next step. Okay, that makes more sense to me now. So Fisher E, A, EZ, EAZ. There's probably a few more than that, but
I was going to say, when we get into high pressure valves, that's when we talk about the EH and the EHAs.
Okay, that's a whole other conversation.
Because the H stands for high pressure. I know, we're just so intuitive.
That's pretty smart. You know what, I'll share with you. I feel like I might have said this on an earlier episode, but so Rosemount likes to get a little bit funny with some of their model codes too sometimes. So up in Canada, we have pretty cold climates, and so if you want to get an extended ambient condition, I believe it's to -50 F. It's the option code BR for burr. And I think there's a burr 4 and a burr 5, depending on how cold, like -40 or -50. So I always laugh at that one too. I go, yeah, that was a good choice for that model code option. So
we have the same kind of thing. So I was talking about noise attenuation.
Yep.
So stopping that noise from occurring, we call those the whisper trims.
Ah, okay. I've heard of those. Yeah, those ones are pretty funny. Whisper trim for noise. Oh, I guess I can't forget that. Okay, so actually that brings up to my next question about trim. So I understand you have a valve body, and I understand you have, I guess, a plug and a stem to kind of vary how big that orifice is. Then what's this trim? Where does that fit into things?
So we're talking about the body. So in an E-body, an EZ, an ES, an ET, and an ED all use the same body shape.
Okay.
And then each of the trim components, that's where we have a plug stem assembly. So the plug is what moves up and down inside the cage.
Yep.
The cage is what's characterized to control the flow. The plug allows more, and that's kind of like opening and closing your sink more. It goes up and down, or it rotates, and that's what allows the flow through. And then that will seat against our seat ring or a seating surface, and that's what provides the leakage rates. So between those seating surfaces and the edge of the plug, that's what determines how much flow comes through.
Okay.
And then the cage determines what that actually looks like. So if we've got some of those severe service applications, if it's cavitating, we might have a cavitrol cage, which will help to control the pressure drop as it comes through the valve to avoid cavitation from occurring.
Gotcha.
Or we'll have those whisper trims that have the custom design holes to reduce the noise that's actually going to be occurring as the valve travels up and down.
Gotcha. Okay, and I feel like I've heard, so with the cage itself, that's basically what the the plug and stem sit in and what the flow travels through that cage. But that cage itself can be different shapes, right? I think there's like an equal percent and there's quick opening. And so it varies, I guess, if I have it at my understanding correctly. So if it's fully seated and when you just open it a little, well, that, depending on what cage you have, it lets more or less flow. So it could be the same valve and everything, but just that cage changes the performance. Is that right?
100%.
Hey, I got something right.
And what's really cool as well is that if a customer starts using that cage in a different, using that valve in a different way, we can just switch out that trim set without removing the body. Sometimes we only need to replace the cage. Sometimes we need to change the whole trim set. Depends on how things change. So if you suddenly need to be able to flow more process than you were before, we can redesign. So we could move you from a linear cage to a modified equal percent.
Gotcha.
And that means that you would get more flow earlier.
Gotcha.
Or we could move you to a quick opening, which means that you get a lot of flow right in the beginning, and then you get better, tighter control as you open up further. Okay. So it depends on how you need to operate your plant and what your process is as to what kind of trim design we would give you. Gotcha.
And I feel like the quick opening cage, I think I saw that at the Emerson Exchange. They had this massive valve there that I think was supposed to be used for surge protection. So and then the whole thing was, this giant, I don't know how big it was, maybe 4 feet. It was a massive valve, and it could open in like 1 second or like 1.5 seconds. Yeah, and it was this big loud thing on the floor that was like, shh, 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 and everyone was like, what the heck is that? And the Rosemount side was making no noise, so we were a little jealous, but I guess that's probably that quick opening one that you're describing.
Yep, and so those are actually really cool. Because for anti-sedge applications, typically you want to stop the plant from going into a trip scenario.
Yep.
And so it needs to move really fast, really quickly so that things don't go badly.
Gotcha.
Problem with those is that they're also trying to flow typically a gas. And gases moving very quickly make a lot of noise. So that was actually a custom design quick opening whisper trim.
Oh, wow.
So that it wasn't making as much noise as it should.
Oh, I still thought it was loud. So maybe I missed the point. I'm like, this thing is bloody loud. And they go, well, it's actually the quietest one we could have made.
But that's the difference between a plant environment and like
a trade
Emerson
floor.
Exchange, which is a trade floor.
Yeah.
Because that trim set is only making, 84 dBA. We're below the 85 dBA with that construction.
Okay.
Whereas in a fully pressurized gas service, if we had just a normal trim, no whisper, you're looking at very scary numbers.
Gotcha.
Like louder than a jet engine taking off.
Oh, really?
So it was loud for what we were expecting.
Okay,
to be.
so my Apple Watch would go off and tell me I'm in a noisy environment. Is that right?
Oh, heck yeah.
Yeah, it's funny. That always happens when my dog is barking. I'm going, well, my watch isn't too happy you're barking. Can you quiet it a little to under 90 dB, please? That's funny. So that's something that I don't think we talk about on the instrumentation side because it doesn't really have an impact is the noise piece. And I never really, I think, appreciated how much that was considered. So do you have certain thresholds that you're trying to target and you're trying to reduce to?
So there's typically 2 pieces of the bracket. So we as humans can only hear a certain amount of noise for a certain period of time before it starts to cause us long-term damage.
Yep.
And so OSHA has actually set that to 85 dBA.
Okay.
So you can listen to 85 dBA's worth of noise for 8 hours without significant hearing loss long term.
Gotcha.
And so that's about, I'm trying to remember what the actual description was. I think it's like children in a school environment. You know how kids get pretty loud?
Okay, yep.
Or like a very busy office environment, consistent noise. Like that's the kind of things that we have no issues with. Once you get past that point, that's when you can start to see longer-term health issues. And so that's why if you ever go to a plant environment, they'll give you safety protection. They'll give you earmuffs. They'll give you earplugs so that you're not having to be exposed to those louder noises.
Gotcha.
By providing that safety procedure, you're actually increasing how much noise you can technically listen to for a longer period of time without causing yourself damage. So that's the human piece of it.
Yeah.
So depending on how much humans are going to be involved with this specific area will depend on what the noise requirements are. So if you are going into a plant that's actually, or if you're going into the middle of nowhere, plant in the middle of nowhere, in the middle of the desert, that's mostly automated and people don't go out there.
Yeah.
There might not be limitations on noise from a human perspective. Whereas if you're looking at like a gas sampling station in the middle of a city next to a children's park.
Yeah.
Okay, technically we don't have to do you have to limit it to 85 dBA, but really people want it to be even less than that.
Gotcha.
So we might have more limitations.
You might still get complaints at 85,
yep.
right? Gotcha.
So that's the human piece of it. And then there's a structural piece of it as well. So we do have upper limits of, in that environment where we're a plant in the middle of nowhere and no one goes and looks at it, what's the maximum noise?
Yeah.
Well, the maximum noise is going to be a vibrational-led mechanical piece.
Interesting.
So too much noise creates vibration,
yep.
and then that can cause damage to the actual structure and stop things from working.
Yeah, or maybe the valve kind of, I don't know if this happens in valves, they kind of not fall apart, but they kind of loosen, right? Like I know in some applications I've seen where like just like on the wiring on like the conduits, it can kind of just fall off because it's such high vibrations that I don't know if that same problem happens for control valves. But
so if we don't know that certain things are happening, or if piping's not built correctly, or if you go through an earthquake, that can also cause problems. You're right. And then different pieces can start to vibrate and back off and fall apart. Yep. So that does occur.
Gotcha. Okay. That's pretty cool though to learn about that piece, because I hadn't really thought about it. I know from previous experience, I was in inside sales and I was working on some of our Northern Ontario sales teams where we have customers who are in the middle of nowhere in their pulp and paper or their mines. And I remember hearing the Fisher folks talking about noise, and I remember thinking, noise, right? I mean, they got nobody around them, and sure enough, they had the small town to support the plant, and so of course they care about noise because they live there, right? And they go, well, I don't want to hear this valve at 2 a.m. when I'm trying to sleep, and I was funny because I was thinking, wow, who's complaining? But the people who are living there. So are there any legalities behind it, or is it more just best practice and working with the communities? I guess it depends on where you are too.
So it depends on where you are, what you're trying to do, and what pressures we're looking at. So again, it plays into this piece of the higher the pressure, the more energy there is in the system that's trying to go somewhere. And so that's when you can see those high noise applications. Like most people have regulators on the side of their houses that regulate the pressure of the water that comes into your house, the gas that comes into your house, and those are at lower pressures, and you probably didn't even hear it at any point. Like you live around it and you don't hear it. Yeah. When you look at those higher pressures, even with some of the regulators, high pressure applications, okay, it's usually right next to a control valve, which is making more noise than the regulator, but it is making some kind of noise.
Gotcha. Okay. That makes sense to me. And then, so besides changing the trim, is there anything else? Like I often hear the word like silencers. What's a silencer? How is that part of the valve? Is that addition to the valve?
So there's a number of different ways to reduce the amount of noise that's being produced by the system.
Okay.
And so we typically try to stop the noise from being generated. And so that's why we would change the trim style so that the noise is not generated in the first place. However, if certain situations occur, sometimes you can't stop the noise from being generated, and that noise goes downstream. And so in those situations, we can do something called path treatment.
Okay.
And so path treatment is where you can use a diffuser or a silencer. So a diffuser is basically a plate in the line with designed orifice holes that is designed to produce back pressure onto the control valve so that basically less of a pressure drop is being taken at each of the 2 points, which means that the energy is being distributed in 2 different locations. Now, there's some fun engineering that goes into that.
Yeah.
And you can optimize it for every condition. Yeah. And so diffusers are really good where they need to be. Silencers are a more complex version of diffusers, and I'm not the right person to ask about those. Definitely a good topic for the silencer folks. Okay.
Yeah, see, I don't know where all the limits are, but it's funny, the diffuser that's like right up my alley because, orifice plates are, and I remember folks asking us to I think they just call them pressure reducing plates, or I forget their fancy name. I remember having to size them as an inside sales, and the challenge was it was just a piece of metal you were sticking in your pipe with a fixed hole. So, unlike a regulator where at least you have some, control based on the springs, you had nothing. It was just this fixed thing, and hopefully you have the right pressures going to it. But I guess if it's after a control valve, then that's, or after a regulator or something, then that makes a lot more sense that would actually have a better purpose for that.
So one of the other things we can do as well, like we were saying, diffusers is sized for one condition, and typically that's the noisiest, which is maximum flow, which means it doesn't quite help as much on those minimum flows.
Oh, good point.
So sometimes they can see damage downstream, and if your diffuser plate gets broken, you've lost that downstream back pressure, and
now it's a lot louder.
Now your control valve's making a lot of noise.
Gotcha. Okay.
And so we try and size the two in tandem.
Yeah.
So we want to know both pieces of the equation so that we can help you get the right thing. So another thing that we can do is something called path suppression.
Okay.
And so that's why a lot of customers will use insulation. And so there's two different main kinds of insulation out there. There's thermal insulation, which is I've got a really hot valve and I don't want that heat to get out, or I've got steam, I want to keep that steam in.
Jacketing.
Jacketing, yep.
Okay.
And so, we call it insulation.
We call it jacketing.
So insulation keeps the heat in,
yes.
Fabulous, but it also keeps the noise in as well. But that does mean that the noise is going to travel downstream. So if we've got, we're talking about a valve in the middle of a city.
Yeah.
And we're down to 85 dBA, which is technically requirements. If the valve's going to go, the piping's going to go, underground, or it's going to go out of the public air, we can just put insulation over the top of it, no expensive trim, and that will suppress the noise inside the pipe until it can go somewhere else.
I guess that's the next piece of it too, is that there is a cost to doing all this stuff. And so, the quietest solution might also come with a pretty loud price tag. Whoa, okay. Can I put a box around it? What else? Okay, that makes a lot of sense.
There is another cool piece of technology that we've recently released called the 𝗧𝗜𝗠𝗘, which goes in line, kind of acts, so it fits in as a piece of piping, basically, and so it's a really cool design. I highly recommend that you go on, if you Google 𝗧𝗜𝗠𝗘, you can look at the product bulletin and see the photographs of it. Oh, it's fabulous. Really cool design. What it does is it is designed to target specific frequencies of noise in the process line, and so you can put this in as a piece of pipe after your control valve. Doesn't take a pressure drop, but it can help mitigate the amount of noise that's actually created and passed downstream. So we see these things. They are a really cool piece of new technology. 10 out of 10. Go Google it. They are really cool.
Yeah, it was funny. I just Googled it for those who are listening, and it's basically what she described. I didn't think this was anything too fancy or too exciting. It looked like just a hunk of metal to me, but I guess, I could see the value. That seems pretty cool.
So if you go to the product bulletin, so scroll down.
Go down to here. We're going to give you an educational lesson on how to find the product bulletin. Go to Lakeside Controls, search Fisher 6060 𝗧𝗜𝗠𝗘 model attenuator, and then you'll find the document. What are we looking for in particular? The inside part. Wow.
I know.
Okay, for those, again, who are listening, it's more sophisticated than a hunk of metal. It's a hunk of metal with a lot of holes. Very interesting. And so it comes in this inlet, and comes in the outlet, and this silences it.
Yep, so the process goes straight through the center of it. Just like I said, it is replace a section of pipe. It is the same size internally as a piece of pipe, so you don't lose any pressure, you don't lose any process. And we have these resonant frequency chambers. Okay. And so each of these chambers that he's looking at are actually different sizes, and they're designed to target different frequencies that we can hear.
Oh, cool.
We actually hear it. And so it helps to remove that frequency from the spectrum to reduce the noise downstream. Wow. So if you think about a tuning fork.
Yes.
It operates in the same way, but it's a reverse tuning fork. So
Yeah.
it takes that node out of the process line.
Oh, wow. So again, to describe this to me, this looks like a filleting a fish here. So you got a cross-sectional area of fish, and then the fish gets bigger into the middle and then smaller out to the tail. And then there's these different chambers that, I don't know, there's probably like a dozen or more of these chambers that are different lengths. Okay, so that's what's actually pulling out that frequency. That's pretty cool. Okay, now I see that this being pretty interesting. So this is one technique to help pull out that sound. Okay, that's cool. Now, so we've talked a lot about noise, and we've talked a lot about steam applications and different things that you have to do. I feel like the one piece we haven't talked about is performance. So if I'm someone who wants a control valve, there's a purpose that I want this for, right? I'm not just putting it in for the sake of supporting Lakeside and Emerson. So maybe we could talk a little bit about what do I want as an end user, let's say, out of this valve, and what can you do and change to give me that? And what do I care about, pretending that I don't know?
So it really does depend on what you as a customer want. Do you want a valve that can just control, process, and you've got a sensor upstream that will tell you what the current process conditions are, and it will automatically update, kind of like a regulator, but for different conditions. We can do that. That's one type of product that we can do. The main piece of equipment on a control valve that determines how it operates is what kind of controller you're using. So Emerson uses something like a C1 is a direct controller, in which case it takes a little bit of the upstream and downstream process. You tell it, as the customer, tell it what you want it to be, and it will automatically control at the valve. You don't need fancy computers.
Oh, wow, okay.
It can do it by itself. If you want to have better control from your control booth, that's when we look at something like a digital valve controller, the DVC series. And then depending on how you want that to be operating and how much maintenance you're willing to do on your valve will depend on what tier of DVC we're actually going to suggest. So hot communicating, our HC tier, is going to talk just directly to your control system, and you can do some small interactions, understand what's going on at the valve, and have some good control there. We then have something called AD tier, which is automatic diagnostics.
There's a lot of acronyms. I
was going to say, we're going through quite a few acronyms here. So AD is auto diagnostics, and so that's where you can actually set up an alert in your DVC. So when something starts to go wrong, it will tell you.
That's handy.
Yeah, which is really cool. So we call it the 3 a.m. call. So if something starts to go wrong at 3 a.m., the valve will be like, "Ooh, wait, I'm deviating from my set point."
Interesting.
Or, wait, I'm suddenly taking more air than I used to be taking. It will create an alert, and it will tell you. And you go into the system and look it up, and it'll say, "Hey, I'm taking more air than I used to be taking. Can you take a look at me?" And actually, if it requires more air, maybe our actuator, the thing that actually moves the valve up and down, maybe there's this specific component. Maybe the diaphragm's seen too much heat. And then you can look at it and go, you can go into the DVC and say, yeah, this valve suddenly saw a whole bunch of heat. It got really hot right here. Maybe that's the piece that I need to fix. So that when you go into your maintenance cycle, you actually know what to look for rather than just going in blind or not even knowing that there's an issue at all.
Yeah. That's cool. I can see similar analogies in the measurement world where it's like you have that baseline of what you're looking for, and then you're alerted to deviations. So like we have on our pressure transmitters, we can do a continuous loop check. So we look at the loop and we see, you baseline it for when you install it, and it knows the voltages and the resistance in that loop. And over time, maybe you can have corrosion in the loop, maybe water gets built up where it shouldn't, and so forth. Whatever the reasons are, you might be outputting 12 milliamps, but then by the time it gets to your control system, it might be 14. And you might not know, you might just think, the pressure is high, right? So, but by doing this continuous loop check, it can tell you, wait a second, check the loop here because we're outputting this and you're getting this at your control system. So there's that deviation. So same kind of idea. I think maybe
that's really cool.
Yeah,
I didn't realize that.
Maybe the Fisher folks copied the Rosemount folks, or maybe it was, we can argue where they came from, but it's a cool idea. So, okay, so that makes sense. So, I guess for my layman's terms to understand, I think when it comes to valves, you talked about a few things about having a good performing valve. I think, at least to me, I would think, I guess it does depend on the application, but it's something that could potentially handle a wide range, and maybe get to that set point fast with nominal deviations. I guess those are kind of the things you're balancing, and then obviously paired with noise and price and all the other factors. Yep. But those are kind of the main things that I think go into picking the appropriate valve.
100%. And I like to use a car metaphor here, and I'm sorry if it gets a little bit wonky.
Nope.
But it's just like cars out on the road. There's a whole variety of different products out there, different cars that you could have. And someone that's buying a big truck probably doesn't want a little bitty, teeny, tiny town car, because you want two different products for two different things. Yeah. And just because you've got a big truck doesn't mean that you have the newest truck. True. So you could have an old truck that's 20 years old, or 40 years old, let's say. 40-year-old truck, no communication, no computer on board. And so when it goes wrong, you've got to listen for the noises for something going wrong on the highway. And you got to take it in to get it maintained. Yes. Or you can do the work on it yourself. Gotcha. So that's kind of like one type of controller would be that C1. You got to listen and understand what's going wrong with your truck. You got to know what your valve is, and you got to be paying attention to it.
It depends on how critical it is too, right?
Yep. Whereas some of these newer cars, newer trucks have that onboard diagnostics. Yes. I know that my car has it has onboard diagnostics. Okay, yeah. Which means that when I'm going down the road, I can check my tire pressure. I can see what my battery's at. Fancy. I can see my mileage. And that's kind of like our DVCs with that performance diagnostics. The valve's running. I'm driving the car. Yeah. And I can see some of these features and understand how the car is operating. Now, did I need that back when I was in college? No. Same kind of thing with customers. There are some key valves out there, like those anti-surge valves, that can cause an entire plant to trip if they don't work right and cause a lot of damage. Yeah. You want those valves to have that immediate feedback. Yeah. When half of the other valves probably don't need that feedback. Yeah. And so that's what gives you that high level of accuracy, the understanding of what's going on, and making sure that your guy in the control room is actually able to operate that valve and control so that you can control your process to what you need it to be.
That makes a lot of sense. Okay, now I'm seeing the buddy-buddy relationship between Fisher and Roseman here. I'm seeing the overlap. I'm seeing the analogies. I'm still drinking blue, not green, but we'll see.
We'll convert you one.
Yeah. So you had mentioned something about temperature, and that's probably the last piece I wanted to talk about was the inputs into the valve. So are the Fisher valves taking any direct inputs themselves? Like, are they, like you mentioned, temperature? It's not measuring temperature with an RTD, right? Or is it?
So control valves are specifically designed to control the pressure of the process. Okay. So we look at the inlet pressure and the outlet pressure. Gotcha. However, temperature can make a difference, because if you increase the temperature of the process by 100 degrees, that can drastically change what's actually happening. Gotcha. If you've got water coming in at 0 degrees Celsius and now it's 100 degrees Celsius, you've got steam happening. Gotcha. So we need measurements around to tell us that, okay, this is still what we sized this valve to be at. Gotcha. And then we need more measurements to tell us, okay, what's the inlet pressure, what's the outlet pressure of the system, so that the valve knows where it needs to be operating. Gotcha. Does it need to be more open? Does it need to be more closed?
That makes sense.
Do you need that increased pressure drop or not?
Gotcha. So pressure is probably the preferred. You probably do. So are there limits to how many inputs? So you could give it pressure, you give it temperature, can you give it flow, right?
So when we size and help you guys select the control valve, the 5 things that we really need are the inlet pressure, the outlet pressure, the intended temperature at the inlet. So how hot's it going to be when it comes in? Gotcha. So what's the inlet state, basically? What the process fluid is, and then the flow rate.
There we go. Yeah, critical.
So what we want to do is we need to find out what those conditions are for when you're operating the plant at its max, at its min, at its normal operation. And so then we'll size and design the control valve to meet the needs. So we'll select, okay, you have a safety requirement, which means this thing needs to have a maximum capacity of whatever your safety margin is. When it's open, it needs to be able to be really open, or you need to be able to operate at really low flows as well as normal flows, depending on how that plant operates. And so that's how we choose what trim you will actually need.
Gotcha. Honestly, there's so many analogies to sizing, like a differential pressure flow meter. All those things that you need. The only thing that we're not talking is noise. That's the only thing that we don't talk about is noise. And I think we have less flexibility in terms of you change what the DP transmitter you're attaching it to, so annubars, orifice plates. You can design those and change those, but there are not as many options as changing trims and cages and stems and plugs and all of that piece. Actually, that kind of brings me to the one last thing I did want to talk about was locally here, we hear internally a lot about something called trim cartridges.
Yeah.
Is that something you know about? Can you explain to me what this is? Because it seems pretty interesting from what I've heard of it.
So the trim cartridge is something that we recently released to make life easier.
Okay.
So we were talking about all of the different trim components, and I said that we've got the plug stem assembly that goes in the cage, and you got the seat ring at the bottom of it. Well, there's actually a whole bunch of gaskets that go in there as well, and there's some other soft goods and some other pieces that you need to make sure that fit in the right places. We try and make life as easy as possible, but you never know. And especially if you've got one person that puts the valve in, that valve's living in the plant for the next 40 years. It's never always going to be the same person looking at it.
Good point.
So instead of having, hopefully, one person that knows what they're doing with all of the trim components, we designed this trim cartridge. So instead of all of these different pieces, it's one piece. So all you do, one time you'll take out the old trim, and then you put this one-piece trim construction into the valve.
Gotcha.
And that has it all built in together. It's got the new bonnet that just bolts straight on top, so you don't even have to worry about it. So when you need to maintain it, or you go through your next maintenance cycle, you pop the whole thing out. You can return it to Lakeside and your impact partner, and they're the ones that can help you do maintenance on it, or you can just drop a brand new one in. So rather than spending a whole bunch of time trying to do this replacement and rebuilding, you can just drop it in straight away. And there's actually a really cool video of one of our maintenance guys trying to do a retrofit on a trim that he knew in a normal body. So a standard trim, taking out all the components and then putting all the components back in, replaced, and then a trim cartridge. And the two videos play right next to each other. And we had to speed up the one to match the trim cartridge. It's a really cool video.
Okay, that is. I feel like I've seen that one. That really sells it when it simplifies that. I guess that's the piece that I hadn't really thought about either. Was that for instrumentation at least it lasts hopefully a long time, but it's mostly repair by replacement, right? It's you get 10, 15 years, then replace it. That I guess is a big delta too. Is part of the maintenance cycle for control valve is replacing some of these pieces that get damaged or just they've had their 10-year lifespan or 15 or whatever it is. So I guess
hopefully more.
Yeah, hopefully more. I'm talking instrumentation, so depending on what it is. So I guess this is something that actually simplifies that because it's you just stock this one thing, drop it in.
Yep, and the really nice thing about these as well is a lot of plants, when they come down for a maintenance cycle, you don't want to be down for a lot of time because you're losing money for every minute that you're not operating.
That's a good point.
So if you're able to save 20 minutes of trying to pull multiple pieces out and put multiple pieces in by just one piece out, one piece in, that can make life a lot simpler. As well as we're seeing aging out in the field, and so a lot of the old guys who actually helped build the plants back in the day were now training up their replacements who don't have as much time out in the field.
Yes.
And so if you can trust a newbie to work on these simple trim cartridges, they can knock a lot of those out, and then you can spend the time that you need to on the real problem valves.
That's a good point. Yeah, and I'm sure, too, some of these valves are not just on water and steam. They're on nasty chemicals, and the less time you spend touching them, the lower your risk is that you're going to get exposed to that chemical. So
exactly. Safety is a choice.
Yeah. Lots of good reasons. Lots of good reasons. Actually, there's one more thing. I know I keep saying that. There's one more thing I want to ask you about, only because you mentioned it, and I actually had fun playing with it, was that if you're interested in learning more about severe service, there's an app, is there?
Yeah, so it's not even just for severe service.
Oh, okay.
It's just that the severe service team helped put it together.
Ah.
And so it's an app that's available in the Google Play Store and the Apple App Store.
Gotcha, yeah.
And it's called the Severe Service app.
Cool.
You don't need to add Fisher or Emerson or anything else, just Severe Service.
Gotcha.
Really cool application. On the main screen, there's 4 different options that pop up. And so you can do a basic CV calculation.
Cool.
So if you're looking at a valve or you're looking at a process and you're not quite sure what's going on inside, or if you've got a quote from Lakeside and going, oh, I didn't know my CV was that high, you can do a double check yourself and just make sure that everything's going okay.
That's cool. And I think the example I had fun playing with it was telling us the valve might be cavitating.
Yeah.
So it gave us a little bit of a warning to just go, well, maybe something's going on here. Maybe I'm asking for too much, or I gave the wrong data to Lakeside.
No, it's really cool because exactly as you said, it will give you those warnings. So if you're in a severe service application like cavitation, flashing, or noise, it'll give you that warning.
That's great.
Tell you what's going wrong, and then there's a learn more button.
Oh, no way.
And so it will take you to a page which will explain what the phenomena is.
Wow.
There are videos that show you what that actually looks like in lines. So with cavitation, there's a really cool demo, and you can hear the rocks flowing.
Oh, wow.
There's also a whole bunch of documentation out there on like which applications we see these in most commonly, what kind of products are out there on the market. If you are in a specific industry, we have source books available on the app as well.
Cool.
And so you can look through every different part of a process and what we would be seeing in the industry and what's the industry standard for products. So it's a really cool resource. It's my favorite thing.
I was going to say, we got to step it up on the measurement side. I don't think we have something like that. That's pretty cool. That's great. Okay, well, thank you so much for your time. Really appreciate it. Again, for those who are listening, if they wanted to connect with you or learn more information, how would they go about doing that?
Well, come through Lakeside first.
Yeah, I like to hear that.
So we're here at the factory, so we're not the most social people.
I thought you were pretty social.
So come through Lakeside, and you guys can help get in contact with us.
Yeah.
And that's the best way of getting through to us.
Yeah, fantastic. And then, hey, if we have something really complicated, we have to get Emily, we absolutely will. Yeah. Okay. Well, thank you so much. Hopefully you enjoy your stay in Toronto and really appreciate your time on the show today.
I will do, eh?
Take care.
Bye.